is Valerie, and I read stuff on the internet before bed, but you can join me. Today, I want to read something about astronomy. I think it's extremely interesting topic. Let's start with basic astronomy. So we can get on Wikipedia and see what we can find here. Not really much actually. Oh no, there is something. Astronomy comes from a Greek word and it literally means the science that studies the laws of the stars. Astronomy is a natural science that studies celestial objects and phenomena. It uses mathematics, physics, chemistry in order to explain their origin and evolution. Objects of interest include planets, moons, stars. Galaxies, comets, nebulae. What's that? Let's look what's nebulae. It comes from Latin for clouds or fog, and nebula is an interstellar cloud or dust. Hydrogen, helium, and other ionized gases. Term nebula originally was used to describe any diffused astronomical object, including galaxies, beyond Milky Way. The Andromeda Galaxy, for instance, was once referred to as the Andromeda Nebula, and spiral galaxies in general as spiral nebulae. Before the true nature of galaxies was confirmed in the early 20th century by Vista Sliver, Edwin Hubble, and others. Okay, let's get back to astronomy. Relevant phenomena include supernova, explosions, gamma ray bursts, quasars, blazars, pulsars, and cosmic microwave background radiation. More generally, astronomy studies everything that originates outside Earth's atmosphere. Cosmology is a branch of astronomy. It studies the universe as a whole. Astronomy is one of the oldest natural sciences. The early civilizations in recorded history made methodical observation of the sky. These include the Babylonians, Greeks, Indians, Egyptians, Chinese, Maya, and many ancient indigenous people of the Americas. In the past, astronomy included disciplines as diverse as astrometry, celestial navigation, observational astronomy, and the making of calendars. Nowadays, professional astronomy is often said to be the same as astrophysics. Professional astronomy is split into observational and theoretical branches. Observational astronomy is focused This is especially true for discovery and observation of transient events. What's that? Let's look that up. A transient astronomical event, often shortened by astronomers to a transient, is an astronomical object or phenomenon whose duration may be from seconds to days, weeks, or even several years. This is in contrast to timescale of the millions or billions of years during which the galaxies and their component stars in the universe have evolved. Singularly, the term is used for violent deep sky events such as supernovae, novae, dwarf nova, outbursts, gamma ray bursts, and tidal disruption events, as well as gravitational microlensing, transit, eclipses, and comets. These events are part of the broader topic of time domain astronomy. Let's go and see what is deep sky. Deep sky object is any astronomical object that is not an individual star or solar system object such as moon, sun, planet, comet. The classification is used for the most part by amateur astronomers to denote visually observed, faint naked eye and telescopic objects such as star clusters, nebulae, and galaxies. So deep sky goes for something like star clusters when it's not individual. Interesting. The distinction of deep sky is practical and technical, implying a variety of instruments and techniques appropriate to observation and does not distinguish the nature of the object itself. Okay, coming back to astronomy again. Amateur astronomers have helped with many important discoveries, such as finding comets. History of astronomy. Ancient times. In early historic times, astronomy only consisted of the observation and predictions of the motions of objects visible to the naked eye. In some locations, early cultures assembled massive artifacts that possibly had some astronomical purpose. In addition to their ceremonial uses, these observatories could be employed to determine the seasons, an important factor in knowing This is known as the geocentric model of the universe, or the Ptolemaic system, named after Ptolemy. A particularly important early development was the beginning of mathematical and scientific astronomy, which began among the Babylonians, who laid the foundations for the later astronomical traditions that developed in many other civilizations. The Babylonians discovered that lunar eclipses recurred in a repeating cycle known as Saros. Let's look what is Saros. Saros is a period of exactly 223 synodic months, approximately 6,585.3211 days or 8 years, 11 days, 8 hours that can be used to predict eclipses of the Sun and Moon. One Saros period after an eclipse, the Sun, Earth and Moon return to approximately the same relative geometry, a near straight line, and a nearly identical eclipse will occur in what is referred to an eclipse cycle. A Sar is one half of a Saros. A series of eclipses that are separated by one Saros is called a Saros series. It corresponds to 223 synodic months. The 19 eclipse year means that if there is a solar eclipse or lunar eclipse, then after one Saros, a one moon will take place at the same node of the orbit of the moon, and under these circumstances another eclipse can occur. The earliest discovered historical record of what is known as the Saros is by Chaldean Neo-Babylonian astronomers in the last several centuries BC. It was later known to Hipparchus, Pliny, and Ptolemy. The name Saros was applied to the eclipse cycle by Edmund Halley in 1691, who took it from the Suda, a Byzantine lexicon of the 11th century. The Suda says, the Saros is a measure and a number among Chaldeans. For 120 Saroi make 2,220 years of 12 lunar months, according to the Chaldeans. Reckoning if needed, the Saros makes 222 lunar months, which are 18 years and 6 months. Years of 12 lunar months. The information of the Suda in turn was derived directly or otherwise from the Chronicle of Eusebius of Caesarea, which quoted Berosus. We're coming back to history of astronomy again. So, following the Babylonians, significant advances in astronomy were made in ancient Greece and the Hellenistic world. precession. Precession is a change in the orientation of the rotational axis of a rotating body. In an appropriate reference frame, it can be defined as a change in the first Euler angle, whereas the third Euler angle defines the rotation itself. In other words, if the axis of rotation of a body is itself rotating about a second axis, that body is said to be precessing about the second axis. A motion in which the second Euler angle changes is called nutation. In physics, there are two types of precession, torque-free and torque-induced. In astronomy, precession refers to any of several slow changes in an astronomical body's rotation or orbital parameters. An important example is the steady change of the orientation of the axis of rotation of the Earth, known as the precession of the equinoxes. Not really clear what it is for me, but okay. So, we're coming back to the history again, and we are going to the Middle Ages. Medieval Europe housed a number of important astronomers. Richard of Wallingford made major contributions to astronomy and horology, including the invention of the first astronomical clock, the rectangulus, which allowed for the measurement of angles between planets and other astronomical bodies, as well as an equatorium called the Albion, which could be used for astronomical calculations, such as lunar, solar, and planetary longitudes, and could predict eclipses. Nicole Ores and Jean Buridan first discussed evidence for the rotation of the Earth. Furthermore, Buridan also developed the theory of impetus, predecessor of the modern scientific theory of inertia, which was able to show planets were capable of motion without the intervention of angels. It's Middle Ages. I'm not sure what they believed in. Able to show planets were capable of motion without intervention. Let's go to the... Yeah, it's probably angels because it's God's philosophers how the medieval world laid the foundation of modern science. But I'm not sure. George von Bierbach and Richie Montanus helped make astronomical progress instrumental to Copernicus' development of the heliocentric model. Decades later, astronomy flourished in the Islamic world and other parts of the world. This led to the emergence of the first astronomical observatories in the Muslim world by the early 19th century. In 964, the Andromeda Galaxy, the largest galaxy in the local group, was described by the Persian Muslim astronomer Abd al-Rahman al-Sufi in his book of fixed stars. The SN 1006 supernova, the brightest apparent magnitude stellar event in recorded history, was observed by the Egyptian Arabic astronomer Ali ibn Ridwan and Chinese astronomers in 1006. Some of the prominent Islamic Astronomers during that time introduced many Arabic names now used for individual stars. It is also believed that the ruins at Great Zimbabwe and Timbuktu may have housed astronomical observatories. In post-classical West Africa, astronomers studied the movement of stars and relation to seasons, crafted charts of the heavens as well as precise diagrams of orbits of the other planets based on complex mathematical calculations. Songhai historian Muhammad Kari documented a meteor shower in August 1583. Europeans had previously believed that there had been no astronomical observation in sub-Saharan Africa during the pre-colonial Middle Ages, but modern discoveries show otherwise. For over 6 centuries, from the recovery of ancient learning during the late Middle Ages into the Enlightenment, the Roman Catholic Church gave more financial and social support to the study of astronomy than probably all other institutions. Among the Church's motives was finding the date for Easter. Scientific revolution. During the Renaissance, Nicolaus Copernicus proposed a heliocentric model of the solar system. His work was defended by Galileo Galilei and expanded upon by Johannes Kepler. Kepler was the first to devise a system that correctly described the details of the motion of the planets around the Sun. However, Kepler didn't succeed in formulating a theory behind the laws he wrote down. It was Isaac Newton, with his invention of celestial dynamics and his law of gravitation, who finally explained the motions of the planets. Newton also developed the refractoring telescope. Improvements in the size and quality of the telescope led to further discoveries. The English astronomer John Flamsteed calculated over 3,000 stars. More extensive star catalogue was produced by Nicolas Louis de Cassily. The astronomer William Herschel made a detailed catalogue of nebulosity and clusters, and in 1781 discovered the planet Uranus, the first new planet found. So Uranus was discovered only in 1781. During the 18th, 19th century, the study of the three-body problem by Leonard Euler, Alexis Claude Clairaut, and Jean Lerond d'Alembert led to more accurate predictions about the motions of the Moon and planets. This work was further refined by Joseph Louis Lagrange and Pierre-Simon Laplace, allowing the masses of the planets and moons to be estimated from their perturbations. Significant advances in astronomy came about with the introduction of new technology, including the spectroscope and photography. Joseph von Fraunhofer discovered about 600 bands in the spectrum of the Sun in 1814-15, which in 1859 Gustav Kirchhoff ascribed to the presence of different elements. Stars were proven to be similar to the Earth's own Sun, but with a wide range of temperatures, masses, and sizes. The existence of the Earth's galaxy, the Milky Way, as its own group of stars It is produced, for example, in synchrotrons using bending magnets, undulators, and/or wigglers. In the particle, if the particle is non-relativistic, the emission is called cyclotron emission. Okay, that sounds like physics that is not easy to understand right away. Let's come back to what we read before. So radio galaxies are quite not really understandable on the intuitive level for me. So okay, that's fine. So physical cosmology. We're coming back to the history, and physical cosmology made huge advances during the 20th century. In the early 1900s, the model of the Big Bang theory was formulated, heavily evidenced by cosmic microwave background radiation, Hubble's law, and the cosmological abundances of elements. Space telescopes have enabled measurements in parts of the electromagnetic spectrum normally blocked or blurred by the atmosphere. In February 2016, it was revealed that the LIGO project had detected evidence of gravitational waves in the previous September. Let's go and look what is LIGO project. The LIGO is the Laser Interferometer Gravitational Wave Observatory. It is a large-scale physics experiment and observatory to detect cosmic gravitational waves and to develop gravitational wave observation as an astronomical tool. Two large observatories were built in the United States with the aim of detecting gravitational waves by laser interferometry. These observatories use mirrors spaced 4 kilometers apart, which are capable of detecting a change of less than 1/10,000th the charge diameter of a proton. So the location is in Hanford side, Washington, and Livingston, Louisiana, US. Its length is 4,000 meters, 4 kilometers. Okay. The initial LIGO observatories were founded by the National Science Foundation and were conceived, built, and are operated by Caltech and MIT. They collected data from 2002 to 2010, but no gravitational waves were detected. The Advanced LIGO project, LIGO project to enhance the original LIGO detectors, began in 2008 and continues to be supported by the NSF, National Science Foundation, with important contributions from the United Kingdom Science and Technology Facilities Council, the Max Planck Society of Germany, and the Australian Research Council. The improved detectors began operation in 2015. The detection of gravitational waves was reported in 2016 by the LIGO Scientific Collaboration and the Virgo Collaboration, with the international participation of scientists from several universities and research institutions. Scientists involved in the project and the analysis of the data for gravitational wave astronomy are organized by the LSC, which includes more than 100 scientists worldwide, as well as 440,000 active Einstein home users as of December 2016. LIGO is the largest and most ambitious detections of gravitational waves. Maintenance and upgrades of the detectors are made between runs. The first run, which ran from September 12, 2015 to January 19th, 2016, made the first 3 detections, all black holes mergers. The second run, which ran from November 30th, 2016 to August 25th, 2017, made 8 detections, 7 black hole mergers and the first neutron star merger. The third run, it is divided so far into O3A, which lasted from April 1st to September 30th, 2019, and O3B, which lasted from November 1st, 2019 until it was suspended in March 2020 due to COVID-19. I would like to read more about gravitational waves. Do you agree? Gravitational waves are disturbances in the curvature of space-time generated by accelerated masses that propagate as waves outward from their source at the speed of light. They were proposed by Henry Poincare in 1905 and subsequently predicted in 1916 by Albert Einstein on the basis of his general theory of relativity. Gravitational waves transport energy as gravitational radiation. Okay, again, gravitational waves transport energy as gravitational radiation, a form of radiant energy similar to electromagnetic radiation. Newton's law of universal gravitation, part of classical mechanics, does not provide for their existence, since that law is predicted on the assumption that physical interactions propagate instantaneously at infinite speed, showing one of the ways the methods of classical physics are unable to explain phenomena associated with relativity. Gravitational wave astronomy is a branch of observational astronomy that uses gravitational waves to collect observational data about sources of detectable gravitational waves such as binary star systems composed of white dwarfs, neutron stars, and black holes, and events such as supernovae and the formation of the early universe shortly after the Big Bang. So, let's look for more about gravitational wave astronomy. I think it's interesting. Gravitational waves have a solid theoretical basis, founded upon the theory of relativity. They were first predicted by Einstein in 1916, although a specific consequence of general relativity. They are a common feature of all theory of gravity that obey special relativity. However, after 1916, there was a long debate whether the waves were actually physical or artifacts of coordinate freedom in general relativity. This was not fully reasoned until 1950s. Indirect observational evidence for their existence first came in the late 1980s from the monitoring of the Hall's-Taylor binary pulsar discovered 1974. The pulsar orbit was found to evolve exactly as would be expected for gravitational wave emission. burst was detected by the orbiting Fermi Gamma Ray Burst Monitor on 2017 August 17, triggering an automated notice worldwide. 6 minutes later, a single detector at Langford LIGO, a gravitational wave observatory, registered a gravitational wave candidate occurring 2 seconds before the gamma ray burst. physics for showing that the orbital decay of the pair of neutron stars, one of them a pulsar, fits general relativity's prediction of gravitational radiation. Subsequently, many other binary pulsars, including one double pulsar system, has been observed, all fitting gravitational wave predictions. In 2017, the Nobel Prize in Physics was awarded to Rainer Weiss, Kip Thorne, and Barry Parish for their role in the first detection of gravitational waves. Gravitational waves provide complementary information to that provided by other means. By combining observations of a single event made using different means, it is possible to gain a more complete understanding of the source's properties. This is known as multi-messenger astronomy. Gravitational waves can also be used to observe systems that are invisible or almost impossible to detect, to measure by any other means. For example, they provide a unique method of measuring the properties of black holes. Gravitational waves can be emitted by many systems, but to produce detectable signals, the source must consist of extremely massive objects moving at a significant fraction of the speed of light. The main source of a binary of two compact objects. Example systems include compact binaries made up of two closely orbiting stellar mass objects such as white dwarfs, neutron stars, or black holes. Wider binaries, which have lower orbital frequencies, are a source for detectors like LISA. Closer binaries produce a signal for ground-based detectors like LIGO. Ground-based detectors could potentially detect binaries containing an intermediate mass black hole of several hundred solar masses. Supermassive black hole binaries consisting of two black holes with masses of 10 in the fifth to 10 in the ninth solar masses. Supermassive black holes are found at the center of the galaxies. When galaxies merge, it is expected that their central supermassive black holes merge too. These are potentially the loudest gravitational wave signals. The most massive binaries are a source for PDAs. Less massive binaries, about 1 million solar masses, are a source for space-borne detectors like LISA. Extreme mass radio systems of a stellar mass compact objects orbiting a supermassive black hole. These are sources for detectors like LISA. Systems with highly eccentric orbits produce a burst of gravitational radiation as they pass through the point of closest approach. Systems with near-circular orbits, which are expected toward the end of the spiral, emit continuously within LISA's frequency band. Extreme mass radio in spirals can be observed over many orbits. This makes them excellent probes of the background space-time geometry, allowing for precision tests of general relativity. In addition to binaries, there are other potential sources. Supernova generate high-frequency bursts of gravitational waves that could be detected with LIGO or Virgo. Rotating neutron stars are a source of continuous high-frequency cosmic strings are hypothetical one-dimensional topological defects which may have formed during a symmetry-breaking phase transition in the early universe, when the topology of the vacuum manifold associated to the symmetry breaking was not simply connected. It is expected that at least one string per Hubble volume is formed. Their existence was first contemplated by the theoretical physicist Tom Kibble in the 1970s. The formation of cosmic strings is somewhat analogous to the imperfections that form between crystal grains in solidifying liquids or the cracks that form when water freezes into ice. The phase transitions leading to the production of cosmic strings are likely to have occurred during the earliest moments of the universe's evolution, just after cosmological inflation, and are a fairly generic prediction in both quantum field theory and string theory models of the early universe. Okay, this is a very theoretical thing, but it's still interesting. And what else about gravitational waves? So we can find cosmic strings if they exist with gravitational waves, but we haven't yet. And that is fine. Okay, gravitational waves interact only weakly with matter. This is what makes them difficult to detect. It also means that they can travel freely through the universe and are not absorbed or scattered like electromagnetic radiation. It is therefore possible to see to the center of dense systems like the cores of supernovae or the galactic center. It is also possible to see further back in time than with electromagnetic radiation, as the early universe was opaque to light prior to recombination but transparent to gravitational waves. The ability of gravitational waves to move freely through matter also means that gravitational wave detectors, unlike telescopes, are not pointed to observe a single field of view but observe the entire sky. Detectors are more sensitive in some directions than others, which is one reason why it is beneficial to have a network of detectors. Directionalization is also poor due to the small number of detectors. An effect of detecting gravitational waves in cosmic inflation. Cosmic inflation is a hypothesized period when the universe rapidly expanded during the first seconds after the Big Bang. Not really seconds, like half and half, like very small fraction of seconds, and would have given rise to gravitational waves that would have left a characteristic imprint in the polarization of the CMB radiation. It is possible to calculate the properties of the primordial gravitational waves from measurements of the patterns in the microwave radiation and use those calculations to learn about the early universe. As a young area of research, gravitational wave astronomy is still in development. However, there is consensus within the Listeners should also be able to listen to the same kind of sources from the early universe as ground-based detectors, but at even lower frequencies and with greatly increased sensitivity. Detecting immediate gravitational waves is a difficult endeavor. It involves ultra-stable, high-quality lasers and detectors calibrated with a sensitivity of at least, very sensitive, as shown at the ground-based detectors GEO 600. It also been proposed that even from large astronomical events such as supernova explosions, these waves are likely to degrade to vibrations as small as an atomic diameter. Okay, so it was interesting. I haven't finished reading about astronomy.